All right. So today we're going to start talking about the decibel. You've probably heard about a decibel before, but maybe you don't actually know what it means. That's what we're going to figure out today. So the reason that decibels exist is because there is a really huge difference between the quietest sound that we can hear and the loudest sound our ears can tolerate. A pretty big difference. In fact, that difference is about 1 trillion if measured in actual air pressure. Because we know that's what sound is now, right? That's air pressure amplitude. So if you compare the smallest air pressure amplitude that will result in our ears hearing something and the highest air pressure that our ears can sort of like handle without blowing up, it's 1 trillion measurements of pressure, okay? Well, that's a pretty big number. 1 trillion is a big number. And we don't like big numbers. And so we have created decibels to help us turn those big numbers into little numbers that are easier for us to deal with. So let's start by looking at it in terms of power. And what I mean by this is that we represent sound in lots of different ways. We work with sound not just in air pressure amplitude. We also work with it in audio format where it's converted to electricity. Okay? Sometimes it's even converted to digital numbers. And sometimes you can measure that electricity with power, how much power it is. Okay? And power can sometimes correspond with amplitude or loudness. Okay? So a decibel is derived using a logarithm. Now, I don't really know how logarithms work, but I know that they collapse big numbers into little numbers, right? I know that much, and that's the part that's important, okay? And so to get a bell, you use a logarithm of 1 power divided by another power. And that will give you what's called a bell. And it's just measuring the difference. So instead of measuring an actual pressure level or an actual power level, instead we just measure the difference between those two levels. That's one of the tricks for collapsing this big, huge range into a smaller range, is we just talk about it in terms of change instead of actual values. So that gives you a bell. And that collapses it down quite a lot, but not quite as much as we would like it to. And so to get what's called a decibel, we derive that by taking 10 times the log of 1 power divided by another power. And deci, of course, comes from the 10 part, right? Now, these are base 10 logarithms. I understand there are other kinds, but the ones that we're going to work with are base 10 logarithms. Now, there's some rules of thumb here for logarithms, for power decibels. And you can kind of calculate them a little bit in your head even. There's a little rule of thumb that I call the 3 and 10 rule. And the 3 and 10 rule is basically, if you multiply the power by 10, you will get a 10 decibel increase, or dB increase, we abbreviate it to. Because we don't like big words either, so we abbreviate everything. So 10 times the power is a 10 dB increase. If you double the power, that's a 3 dB increase. And you can see in the chart on the right how this begins to sort of collapse a really large range of values into a smaller range. So on the left there you have watts ranging from 1 to 20,000. Now, so if we say that 1 watt is 0 dB, or no change, because decibels is a measurement of change, a measurement of difference between two things. So we have no difference yet, we're just starting at 1. So 1 watt would equal 0 dB. Well, if we multiply that by 10, we get 10 watts, and that would be a 10 dB difference. We multiply by 10 again, we get 100 watts, and we get another 10 dB difference. So now we're at 20 dB. We go from 100 watts to 1,000 watts. That's another factor of 10. And we get another 10 dB increase. Now we're at 30 dB. We go from 1,000 watts to 10,000 watts, and that's another 10 dB increase. Now we're at 40 dB. Okay, so we went from 1 to 10,000, a difference of 10,000, and we got 40 dB. Let's do 10,000 again and go to 20,000. That's only a 3 dB increase because all we did was double it. So that first 10,000 was 40 dB. The second 10,000 is only 3. Now, so you can see now how this can be used to take a really large range of values, 1 to 20,000, and turn it into a range of 0 to 43. And that's pretty useful. Okay? Everybody with me so far? Any concerns? Eric?
Well, I just had like one general question.
Yeah.
Is a decibel 10 times a bell?
Yeah.
Yeah. I mean, traditionally, decibel means like 1/10 of something. So why isn't decabel?
Well, because you're actually turning it into a smaller number.
Oh, okay.
Right? So 10 times that logarithm results in a smaller number, not a bigger number. For some crazy reason, because math works that way. That part's not super important for what you need to know, but yes, that's why it's called deci. Okay? Now, here, using that, here's the kind of a chart just showing 0 dB to 10 dB and the corresponding power levels. So you've got 1 watt equaling 0 dB, 10 watts equaling 10 dB, and then all the levels in between. Just another example of how these values collapse. And you can use this to kind of figure some stuff out. So, for example, if I asked you what power level is represented by 80 watts, so how would I express that in decibels? Well, we see that 8 watts is 9 dB, right? And 80 is 10 times that, right? So we would go up 10 dB, and that would be a total of 19, right? So 8 is 9 dB, and 8 times 10 is 80, which is a plus 10 dB, and we were already at 9, so that's 19 dB. See that?
That seems a little too easy.
That's all it is. Okay, let's do another one. What power level is represented by 1 milliwatt in decibels? Well, milliwatt is how many watts? Right? 0.001 watts is a milliwatt. Okay? So, well, we know that when you reduce it by 10, so going from 10 to 1 is a difference of 10 dB. So if we just walk our way down here through these jumps of 10, so we did one jump, that's minus 10. Did another jump, that's minus 10. Did another jump, that's minus 10. So we divided by 10 3 times to get 0.001, right? That's a total of minus 30 dB in power.
It seems like it's going to get so much harder.
It will. It will. We're starting simple, but okay. What about 4 milliwatts? So we know that 1 milliwatt is minus 30 dB, right? So how many dB would be 4 milliwatts? Well, going from 1 milliwatt to 2 milliwatts, we would increase 3 dB, right? So that would be what?
Negative 15 dB.
There it is. What was that? I heard it. Yeah, negative 27. Because we increased 3 dB. Right? Because we're at a negative number. So we add, when you add, okay. So going from 2 milliwatts to 4 milliwatts, that's another doubling, right? So that's another 3 dB increase. So now what do we have? Yeah. All right, there you go. 4 milliwatts equals 24 dB. See how that works? Okay, now, not looking at the notes, I want to rebuild this chart without a calculator using only that 3 and 10 rule. And we will start by labeling 1 watt as 0 dB. Okay? Yep, and we can do 10 is 10. We know that much. So what are the rest of these?
From multiplying 1 by 10.
Yeah. All right, so what are the rest of them?
For like ones in between, or let's do like ones in between, like sort of out of order.
Oh, yeah, we do them out of order. So if we go from if we double that 1 watt, we go to 2 watts, and that's how many dB increase?
3.
Okay, so the 2 would go there, right? We go from 2 watts, we doubled again, that's 4 watts, and that's another 3 dB, so there's 4 goes there. And then you double that again, 8 would go there, right? Okay, we got some of them. Now what?
I know there's decibels. What if we just I remember the random ones, but I don't know how to get there.
That's what we're going to do, is we're going to figure out how to get there. Okay? That's the easy ones. Connor's got an idea? There you go. So 10 divided by 5, or divided by 2, would be 5, right? So that's cutting it in half. You lose 3 dB, so what's 3 dB less than 10? 7. So that's where the 5 goes, right? The 2.5 would go there.
Divide that by 2. Yeah.
Right?
Now
Okay. Those are all the easy ones. These last 3 are tricky. How do we get these last 3? Don't look at the notes. I mean, you know what the answer is going to be if you look at the notes, but it doesn't tell you how to get there. I want to know how you get there. Hmm? No, I want you to look at it for a minute and see if someone figures it out. Anybody see it yet? Yep. Yep.
Is 5 3.25?
Why would you think it's 3.25?
I don't know how to explain my thought process that I went through to get there, but
Okay, but no calculators allowed.
oh, I literally forgot. I'm so sorry.
Eric's got an idea?
I have a sort of long distance, so
All right.
one method of solving it would be to figure out how you could get like 20 in dB, so that then you could subtract by multiples of 3 each time, and
Yeah.
that'll be 8, 5, and 2.
Okay, you're on to it. You're on the right track. How do we get there?
So you
What did you do?
I was like, oh, so 0.75 is between 1.25 and 2. What if I just added 0.75, 2.5, and then added?
Yeah, no, you can only use that 3 and 10 rule. So you have to figure this all out using just that 3 and 10 rule.
Is 100 in the range? Have you subtracted?
Eric's got the right idea. You're going to have to generate a value you don't need in order to get the ones you do need. So you're going to have to generate a value that's off the chart first, and then you can use that to get you the rest of the numbers.
What numbers do you get that range?
And you just have to guess what
It's not a guess. It's not a guess at all.
how is it not a guess?
No one's got it?
I feel like it's like
It's partially
once
there.
once you're gonna say it, it's gonna make so much sense to me.
Yeah.
Like to get there, homie, I don't know, man.
All right, I'm going to give you one more minute, and then I'm going to give it to you.
But where would I have gotten? I don't know where I just got that number from.
Connor's got it?
If you go from 1 dB multiplied by 10 on both sides, that's how that 10 works. Give you 12 and a half watts for 1 dB.
There you go. Okay.
Subtract 3
Yep.
and half.
So if we take that 1.25 and multiply it by 10, we get 12.5, which equals 11 dB, right?
That was so
Wait, I think
smart.
I also had the right answer, but I was using the larger number.
Yeah, you were just going too far. More.
Well, I mean, it's never no harm. Well, it isn't any harm if you have to do longer math.
Yeah. It just takes you longer. But there you go. So now we can go from the 12.5, and what's that divided by 2?
6.25. See, I got 6.25, but I didn't know where.
And that would be 3 dB less than 11.
That would be 8.
Yep. So there's 6.25.
And then go down.
What's 3.25 divided by 2?
3.25 divided to 1.3.
3.125.
Wait, he said 3.
Okay.
Did you mean 6.25 divided by 2?
Yeah, sorry.
Oh, okay,
6.25.
that's
Sorry.
No, it's okay.
6.25. 3.125. So that's going to be our 5 dB. And then 3.125 divided by 2?
1.5625.
It should be 5.625. So we could call it 1.56. That's the interesting thing about decibels, actually. So whether you write 1.6, 1.56, 1.563, 1.5625, all of those are the right answer. All of those equal 2 dB. So there are multiple actual values that can be represented by that decibel. That's how decibels work. Okay? See? It wasn't too bad. Yeah?
You lost me so long ago, it's not even funny.
Okay.
Like way back whenever you were doing the 80 watts
Yeah.
question.
Yeah.
I was lost then and never got back on.
Okay.
Yeah, that's.
I have no earthly idea how you came up with 19.
Okay. So let's go back to that. Come back. Go back. Okay. So we're trying to find 80 watts. Well, we can start by going to 8, from 1 watt to 8 watts. Okay, and that is 9 dB. Okay, so we know that. That chart says that. 80 is 10 times that. Right? So 80 equals 10 times 8. And what happens when you multiply by 10? Goes up 10 dB. So if 8 is 9 dB, 80 is 10 dB more than that, which is 19.
Could you explain the one of the negatives? Because
Yeah.
the jump between like getting to negative 3 and then.
Yeah. So if 1 watt or 1.0 watts is 0 dB, and we have to get to 0.001, well, we do that by dividing by 10 3 times. Okay? So if we go from 1.0 to 0.1, that's a negative 10. Then we divide it by 10 again, we go to 0.01, that's another negative 10. And we know this because we know taking 10 dividing by 10 and going to 1, we lose 10 dB. Okay? So we divide it by 10 again, we get 0.01, That's another 10 dB. That's a total of 30 dB difference that we got.
And then for the next question, you increase by 3,
Yeah.
multiplying it by 2.
Yeah, so then I asked you milliwatts. Well, we know that 1 milliwatt is 30 dB because we just figured that out. And we can figure out 4 by just going up in doubling increments. So we go from 1 to 2, that's a doubling. We go up 3 dB, so that's 27 dB. We go from 2 to 4, that's a doubling again. We gain 3 more dB, we go up to 24. Make sense? All right. And then we just built that using those same methods. We rebuilt it. Okay? All right. Let's try some of these with the calculator now. So, how much louder is 700 watts than 63 watts?
Okay.
Now let's remember the formula for figuring out dB. dB equals 10 times the log of power 1 divided by power 0. Now, so we just need to label these however we want to label them.
Is it always a log base 10?
Yes. So I'll say 700 watts is P1 and 63 watts is P0. It kind of does.
Should you always do the first number as P?
Not necessarily. It just depends on whether you want a positive number or a negative number. So if the big number is on the top, then you're going to end up with a positive number in decibel values. Whereas if the smaller number is on top, you're going to end up with a negative number in decibel values. Either is technically right. It's the same number because you're just measuring a difference. But I'm actually looking for how much louder 700 is than 63. So that implies I want a positive number. But if you put a negative in, I'd give it to you. Right? I mean, because it'd basically still be the same thing. So this is going to be 10 times the log of 700 divided by 63. Okay. Let's get our calculator out. Take a look at this. So here's how you do this on pCalc. I don't know how you do it on your calculator, but here's how you do it on mine. So you do 700 divided by 63. And I get 11.11111 forever. And then I click that log 10 for the base 10 logarithm. And I get 1.045757. And then I multiply that by 10. And I get 10.46 dB. Okay. Anybody else get that? Connor got that? Anybody else? Yep. So you do 700 divided by 63, and you get that answer. And then you take a base 10 logarithm of that, and then you multiply that result by 10.
I feel like you could do that all in one step, but can you?
On some calculators you can. In some calculators you could just like write that whole thing out and it'll give it to you.
I mean, with TI-84s.
Yeah. So yes, if you have a swankier calculator than mine, then yes, you can do that. Okay? Everyone make sure you can do that. Make sure you can do that math with your calculator and get that answer. That's going to be super important.
Jason, can I watch you do it again?
Yep.
Sorry, I feel like every time you go to explain something, I'm writing something down, and by the time I look up,
Okay.
it's 7.
So it's 10 times the log of 700 divided by 63. So I'm going to do 700 divided by 63 first. And I get 11.111.
I'm not really sure if 10 does applies here.
Now I'm going to click the log 10 button to get the base 10 logarithm of that. And I get 1.045757. And then I'm going to multiply that number by 10 times 10. 10.457575. So 10.46. Has everyone been able to get that number with their calculator? How much louder is 10,000 watts than 3,000 watts? Yeah, that was it. That was the answer.
Same thing.
Yeah, it's the same thing. So dB equals 10 times the log of 10,000 divided by 3,000. Okay? So I go here to the calculator, and I do 10,000 divided by 3,000. And I do the log 10 on that. And then times 10. I got 5.23 dB.
Yep.
Everyone else get that?
Can you just pause on the screen for just a second so I
Yep.
can write it down?
I got lost when you did it under us, but it's because mine just have to do that.
Oh, you just type it all in.
Yeah.
I just like to do it a step at a time because that way sometimes people get stuck halfway through. And I can say, oh no, look, here's where we were. Helps you remind yourself of that order of operations.
So in this scenario, P1 will be 10,000.
Yeah.
And P0 is just 3,000.
So you usually want your
Yep. The other way to express it is 10 times the log of the power you ended up with divided by the power you started with. That's another way of thinking about it. Do you need some help, Kat?
No, I just like the log function isn't working on my.
Let me see.
It just says error.
Okay, so clear it out. Okay, so do the 10,000 divided by 3,000.
Right. 10,000 divided by 3.
Okay,
Right.
now hit the log 10 button.
110.
There you go. And now times 10.
I was just doing it wrong.
You got it.
Okay. Incredible.
All right. We ready for the next one? Oh. Okay. So here's a real deal question. Somebody has convinced you that you need an 800 watt amplifier. But you go to the store and you only have enough money to buy the 350 watt amplifier. And you're asking yourself, well, how big of a difference is that going to be? How much quieter is my show going to be if I use that smaller amplifier? That's a big difference between 350 watts and 800 watts. So like, how big of a difference is that going to be in sound? Well, let's figure it out. This will be 10 times the log of 800 divided by 350. All right, you guys are going to do this one. I need 3 answers that are the same.
3.5.
All right, anybody else? I got 2 people that got 3.59. Yep, everyone else. There you go. So it's about 3 dB. So how much is 3 dB? You guys have been doing Sound Gym.
It's a noticeable amount, I think.
It's noticeable, but just barely. Right? Much less than 3 dB, and it's kind of hard to tell if there was a difference, right? So 3 dB is about the difference that your average person can hear without doing ear training. If you do ear training, you can train yourself to hear smaller differences than that, but on your average people, like your audiences that come to see your shows, if you don't change it by at least 3 dB, they are not going to notice a difference. They're not going to notice that you changed anything.
Yeah, on one of the Sound Gym games, like with those fourth faders, if
Yeah.
you just, like get it maybe 3 off,
Yeah.
it might mark it as unacceptable.
Yeah. So, and that's the point, is we're trying to train you to be able to hear better than that. But on average, most people are not going to notice a difference unless it's at least 3 dB. Okay, so what does that tell you? If you buy this cheaper amplifier, it will be a barely noticeable difference in actual sound output. Yeah, and that's if your gain structure is perfect and you're eking every last sound decibel you can out of every last watt, which you're probably not going to do. But But you weren't going to do that with the 800 watt amplifier anyway. So it's still only about a 3 dB difference, right? So, all right, that's a fun one. Someone would pay you money to figure that one out. Okay, so sometimes you got to go the other way. Sometimes you have a decibel difference and you need to go back to the power level. So what if I asked you, find the power ratio of a difference of 13 dB? Power ratio is defined as 10 to the power of the decibel divided by 10. Okay?
That's not an exponent?
It is an exponent. 10 to the power of decibel divided by 10.
Oh,
Decibel divided by 10 is the exponent. Okay? So this is going to be, oops. Let me try this again. So this is going to be 10 to the power of 13 divided by 10. All right, how do you do this on your calculator? Let me show you. So I'm going to first do the 13 divided by 10. I get 1.3. And then hopefully you have or can find this little 10 to the x button on your calculator, 10 to the power of x. And it plugs the number currently in the calculator into that x value. So 10 to the power of x. And I get 19.95. Okay, so that's the power ratio. That's a magic number. 19.95 is the magic number that you can use to figure out 13 dB difference from any power level. So you multiply any power level by 19.95 and you will be given a power level that is 13 dB more than that. Okay? Let me demonstrate. So if you start with 300 watts and you want 13 dB more sound, how much power do you need? Well, you know that the power ratio for 13 dB is 19.95 because you just figured that out. So what is 300 watts times 19.95?
5,985.
Anybody else get that? Yeah. 5,985 watts.
That's the increase that you need that 5,000 plus the original.
No, that's it. No, that's the actual level. So, this is actually a poorly worded question because I'm asking how much more power. So, strictly speaking, you would want to remove the 300 watts from that, and that would be how much more. But that's not I didn't word that very well. I'm actually looking for the actual power level, which is 5,985.
So now it's like if any question is
How much?
asking on
Yeah,
the power ratio level by 13, we can just do times
19.95. Yep. But you also can just, no matter how many dB difference I ask you for, you can find out that power ratio by just doing that little equation, 10 to the power of the dB divided by 10. Okay? Make sense? Okay. Here's another question. If a loudspeaker generates 60 decibels with 2 watts of power, how much power would be required to get to 98 decibels?
Can we pause for a second when I write that down before you
Yep.
start explaining it?
Yeah.
Thank you.
Here's another real deal question someone might pay you money to solve someday. Everybody ready? Okay, so I have to figure out how to make 98 dB, right? Well, I already know how to make 60. It takes 2 watts, right? So I can take that away. And because all I really want to find out is how many more dB do I need. So what's 98 minus 60?
38.
So I'm really looking for a 38 dB difference here, right? Okay, well, what's the power ratio of 38 dB? That's 10 to the power of 38 divided by 10. Anybody know what that is? 6,305, 309.57. Okay, 6,309.57. All right, that's the power ratio of 38 dB. But that is not the answer to my question yet. The answer to my question is, how much power do I need to go from 60 decibels to 98 decibels, which just happens to be a 38 dB difference?
Well, you multiply that by the power which you start with.
Yes, and the power I started with was 2 watts. So 6309 times 2. 619-ish. Okay, that's a lot of watts. There's not many power amplifiers that can do that. We have one in our shop, interestingly enough, but
Have you ever had to use it for a show?
yeah. You can't power it from a 15 amp circuit on the wall. It requires, I believe, at least a 20 amp, if not a 30 amp circuit.
Which amp?
Sounds like an illegal question.
It's not illegal.
Or just saying, like, you really can't do that in a theater, or else you're going to get
Shut up, bro.
Well, I think you might conclude, hey, yeah, that's not reasonable. So maybe let's get a different loudspeaker that makes more sound with less power, right? Yes.
I know Eric explained how we wanted to multiply by 2, but
Yes.
can you just reiterate why
Okay, so remember, power ratio is a magic number. And it's the magic number that represents a certain decibel difference. Okay? So in this case, it was the power ratio of 38 dB, and which is 6,309. That's a magic number. You multiply any power level by that, and you will get a power level that is 38 dB more. Okay? So the reason we multiply by the 2 watts is because that's how much power we already used to get to the 60 dB, right? So we multiply that 2 watts by that number, and we get a power level that is 38 dB more.
Okay.
Yeah?
See, it always makes sense when you explain it, and then I need, and then I'm like,
That's why I have to ask it to be like reiterated
I write it down in
differently.
full sentences.
Okay. That's power. Now let's talk about force.
please tell me stop that power.
Can we take a 5-minute Gatorade hour?
6 is 20 rule versus a 3 and 2.
Yes. Jesse?
What was the amplifier you were talking about that can supply?
It's like a Powerlight 9 or something like that in the shop. If you put it in bridge mono, I think you could get it to do about 12,000 watts into the right, into like a 4-ohm load or something. Okay. So force. Well, force is lots of things. Force can be volts. Force can be pressure. Force can be current. Basically, force is everything except power in sound. Okay? So if you're talking about the power amplifier, then you're dealing with watts and therefore the 3 and 10 rule. Everything else, it follows a different rule, but it's similar. It's called the 6 and 20, which is the same exact thing. It's just when you double a force, you go up 6 dB. And when you multiply a force by 10, you go up 20 dB. Other than that, everything else is the same. There is a formula to derive a force decibel. It's now 20 times the log of one force divided by another force. Okay, but other than that, it's the same math. And then here's the same chart kind of showing you the difference. So going from 1 volt to 10 volts, that's 20 dB. 1 volt to 2 volts, 6 dB. So on and so forth. But same principle, right? We're just going up in 2 dB increments here instead of 1. So let's try this now. Just, futzing around in our head without the calculator and looking at this chart. What is the difference in dB between 2 volts and 10 volts? Well, 2 volts is 6 dB, right? And 10 volts is 20 dB. So what's the difference?
14.
Yeah,
Easy peasy, lemon cheesy.
14 dB.
Well, what if it's without the chart?
Well, then you could figure it out. But that's not what we're doing. We're just using the chart for now. Okay? Let's try another one. What is the difference between 1 volt and 100 volts? Well, 1 to 10 is 20, right? So 1 volt equals 0 dB. 10 volts equals 20 dB. 100 volts is times 10 again. So we go up another 20 dB.
So
40 dB, right?
The way I was
I'm
very
both
on the
with
wrong
you.
side of it, but
The way I was just like,
Yeah, make sure you're multiplying the voltage or the force, not the decibels. You can't do math on decibels. Doesn't work. Well, you can do some math on decibels, but generally you don't, because the decibel is not representing an actual value. It's representing a difference between two values. Okay? All right, let's do the same thing again. So 1 volt equals 0. 10 volts equals 20. Let's figure out the rest.
All right, so if you do like multiply 1 volt by 2.
That gets you the 6.
4 is 12.
Yep, 4 would be there. 8 would be there, right? All right, there we go.
And then divide 10 by 2.
Yep, and you get 5, and that would be the 14.
okay, wait, pause.
Because you divided by 2.
I just kind of only barely heard what Eric said, so I was like, why
So
did I get
10 divided by 2,
Yeah.
that's dividing by 2, you go down 6 dB. So 20 goes down to 14, right?
Gotcha.
Yep, 5 divided by 2 would get you
2.5.
2.5 would be 8, right?
Because then you subtract by 6.
And then divide by 2 again, and you would get 1.2. No.
So then,
Yes, 1.25.
would we follow the same process that Connor did last time and just find the 22?
Yeah. So 1.25 times 10, 12.5, and that gives me a 20 dB increase, which is 22. So 22 dB. And then divide by 2 is 6.25 would be 16. Then 3.125 is the 10. 1.56.
5.6.
There you go. These are the exact same numbers, right?
Yeah.
The ratios are the same.
Though we could have done the long way with the 10.
Yeah, we could have, but all right. If you're going to do it with calculator, here's the formulas. It's all the same. I'm just writing it out 3 different ways for different values. But to derive the decibel, it's 20 times the log of one force divided by another force. And that gets you the dB difference. So it's just 20 times the log instead of 10 times the log if you're working with a force. And if you go in the other direction and you have the decibel difference and you need the force ratio or the voltage ratio or the pressure ratio or whatever, those are all forces, it's 10 to the power of the dB divided by 20 will give you that ratio. And then you use that to multiply against whatever force level you started with, and you will get the actual value. All right. Does that make sense? You ready to do some? What is the dB difference between 2 volts and 63 volts? Well, that's going to be 20 times the log of 63 divided by 2. Okay, let's try it. So I'll go to my calculator, and I will do 63 divided by 2. I get 31.5 log 10. I get 1.498 times 20. I get 29.97. Eric got that? Anybody else get that? Yeah? Lee, did you get that? So it's 20 times the log of 63 divided by 2. Seth, you got that? Okay. Not so bad, right? All right, let's try another one. This is just sort of a gee whiz question, just to show you this doesn't necessarily have anything to do with sound. We use decibels, and the world uses decibels now to talk about the difference between lots of different things. It doesn't have to just be sound. So what's the dB difference between a 9-volt battery and a AA battery? Well, we know, so to do this we need 2 voltages, right? We know the voltages of a 9-volt battery because it's like says 9 volt. Anybody know what the voltage of a AA battery is? Off the top of your head? There you go. 1.5 volts. Okay. All right, so this is just 20 times the log of 9 divided by 1.5. What'd you get?
15.56. Yeah.
Anybody else get that? Kat got that? Eric got that? Okay, must be right. There you go. 15.5 dB difference between a AA battery and a 9-volt battery. So this is important because, again, decibels don't necessarily mean sound. They just mean difference or change. Okay? Okay, we haven't learned about dBu yet. We will next class. So for now, you're going to take this one at face value. There is such a thing called professional line level, and it is +4 dB with a little u, and u just means a reference level. 0 dBu equals 0.775 volts, and therefore how many volts is professional line level? Okay, so I have a voltage value, right? It's right there, 0.775 volts. And I want to know how many volts is 4 dB more than that. Yeah, so I need to know what the force ratio is of 4 dB, don't I? So that's going to be 10 to the power of 4 divided by 20. Anybody got that number?
1.58.
Anybody else get that?
Yep.
Eric got that? Anybody else? Need one more. All right, Thania, you got that? Great, must be right. Okay, so that is the force ratio for +4 dB. So if I want to know how many volts is +4 dBu, I need to multiply that 0.775 by 1.58. So 0.775. So what is 1.58 times 0.775?
I mean 1.2245. Or 0.22. 1.22.
It is officially 1.23. Yes. This is a joke. This is a sound joke. Do you get it?
No.
Check, check. 1, 2, 3. Check, check. Professional line level. We could have picked anything. We picked +4 because it means 1.23 volts, and that's funny. Okay.
Oh, what the fuck? Where's this figure?
There's another way of looking at this, which is when it's air pressure in the air, right? Air pressure amplitude, which is what happens when you actually do sound in the air. Well, when you're putting pressure on the air, that tends to happen equally in every direction, unless you act to make it be different than that. Sound is naturally omnidirectional in most cases. It requires intervention in order to become directional. So you have a certain amount. What's attempting to be diagrammed here is you have a certain amount of energy here in this at this point in space, and that pressure wave is radiating in all directions. And if you sampled that pressure at a given spot, a certain distance away, you would get a certain amount of pressure now. And it would be less than the pressure you started with, because that whole pressure has been distributed across a wide sphere. So it's been divided a lot of times. So the pressure that you measure a little ways away is going to be less because it's been distributed. You go a little farther away now. Let's say you go twice as far away. It's now been distributed even wider. So it's going to be less pressure. Turns out this follows the 6 and 20 rule. So when you double the distance away from a sound, it goes down 6 dB because it's been distributed enough that it drops 6 dB. If you multiply the distance by 10, you drop 20 dB. And this can be calculated using that same math, 20 times the log of one distance divided by another distance. And it will tell you the dB difference between that. So you could do the distance between the front row and the back row. And you would find out how much quieter the back row would be than the front row. Okay? That makes sense? Let's do it. Loudspeaker measures 100 dB at 3 feet. How loud will it be at 30 feet? So the front row is 3 feet away, the back row is 30 feet away. All right. Well, first thing we need to know is what is the dB difference between 3 feet and 30 feet? So that's going to be 20 times the log of 3 divided by 10. And I'm going to do 3 divided by 10 because I want a negative number, because I want to know how much quieter it's going to be. Okay?
Why 3 divided by...
Oh, 30. Sorry, 3 divided by 30. My bad. Good catch. 3 divided by 30. So what's 20 times the log of 3 divided by 30?
Negative.
Yeah, it turns out we could have done this in our head, right? Because it's multiplied by 10. So it's minus 20. It just proves you that the rule works. Okay? All right. So if we have 100 dB at 3 feet, then we will have 20 dB less than that at 30 feet. So what's 100 divided by 20? Or minus 20? 80. So it'll be 80 dB at 30 feet away.
And for that one, you could have just used the rule, right?
Yeah. You okay? Yeah. So you're getting something that could be described as 100 dB at 3 feet away, right? And I say, well, then how loud would it be at 30 feet away? So you need to know the dB difference between 3 feet and 30 feet, because sound gets quieter when you get farther away. Okay? And I just got farther away. So now there's two ways to do this. You could just observe that 30 feet is 10 times more than 3, and therefore, following the 6 and 20 rule, you would know that if you multiply it by 10, you lose 20 dB. Or you could do the math and do 20 times log of 3 divided by 30, and you'd get minus 20. So that's minus 20 dB. You lose 20 dB traveling that distance. So if you start with 100, you lose 20 dB of that going to the back row. You will have 80 dB left when you get to the back row, because you lost 20 of it making the trip.
I understand that, but I don't understand how to put down 20 log.
Yeah, so that's the equation you use to figure out the dB difference between two forces, right? And that same equation works on distance. Okay? So you can put in two different distances, and you will get the dB difference that will result in traveling that distance. Let's try another one, see if it makes any more sense. So a loudspeaker's sensitivity is 113 dB, 1 watt, 1 meter. Guess what? This is how loudspeakers are spec'd. So you read the specifications of a loudspeaker, and they're going to tell you it will generate this many decibels of sound pressure using only 1 watt of power if you measure it 1 meter away. So if you put a sound pressure level meter 1 meter away from this loudspeaker and you put 1 watt of power into it, you get this many dB worth of sound. It's called the sensitivity. How loud will it be with 1 watt at 30 meters? So we're not changing the power level, are we? The power level is staying the same. So I can get rid of that. It's not relevant. What's relevant is the difference between 1 meter and 30 meters. So that's going to be 20 times the log of 1 divided by 30. What is that?
Negative 29.54.
Anybody else get that? Yep. Okay. All right. That's how much we lose by making the trip. Okay. Well, we started with 113, didn't we? So it's 113. Whoop, come back. So it's 113 minus 29.54. And what is that? Say again? Anybody else get that? Connor got that? Reese get that? Yeah? There you go. Somebody would pay you money to solve that for them. I get paid money to solve that every day. Eric's asking for the money now. All right. No, but this is the kind of stuff you do when you're designing a sound system, right? Okay, I buy this loudspeaker, I stick it somewhere. The seats are 30 meters away. How loud is that going to be? And is that loud enough? These are the questions that sound system designers ask themselves. Okay? All right, we're good. Okay, now here's where we get to where the real money is. So here's a actual real loudspeaker made by EAW, Eastern Acoustic Works. They have a loudspeaker that they have named a JF100E. And if you look at the specs for that, they say the JF100E generates 97 decibels worth of sound pressure with 1 watt at 1 meter. How powerful will your amplifier need to be to get 100 dB at 10 meters? Okay, this is a real question here. This is real life. You're going to buy that thing, and you got to put the right amplifier on it in order to make sure you get the right amount of sound out of it. Okay? So, how are we going to figure this out? Well, I would start by saying, okay, if I need 100 dB at 10 meters, how many dB do I need to have at 1 meter coming right out of the loudspeaker? Because I'm going to lose a bunch, right? Making that trip. So, well, yeah, we could do this in our head, right? And we know that the difference between 1 meter and 10 meters is going to be 20 dB. So we are going to need 120 dB at 1 meter. That's terrible writing.
Oh,
Okay.
Yeah, 'cause you're going further away.
Okay, so we're going to need 120 dB at 1 meter. How do I make 120 dB? Well, I don't know, but I know that I can make 97 dB with only 1 watt because EAW said so. Okay, So I just need to know how much more I need. So I can subtract the 97 from that. So what's 120 minus 97?
23.
Anybody else get that? That's right? Okay. So I need to figure out how to make 23 dB more sound, and I got to do it with watts, right? So I need a power ratio of 23 dB. So a power ratio of 23 dB is going to be 10 to the power of 23 divided by 10, right? That's how we get power ratio. So what is 10 to the power of 23 divided by 10? 199.53. Okay. That is the power ratio for 23 dB. So that's the magic number that I use to multiply a power level by in order to get 23 dB more sound. So what was the power level I used to get the 97 dB? 1 watt, right? So I multiply this by 1 watt, and I get 199.53 watts, otherwise known as a 200-watt amplifier. Totally doable, right? Totally doable scenario. Okay. You could get paid money someday to answer that question. Everybody follow that? Yeah. Okay. Not so bad, right? You just got to break it down a little bit. All right, that's it. We're going to do next slide is reference levels, and that's not till Thursday. So we've got a few more minutes. What questions do you have? You want to do any of those again?
Could I watch you do this one again? Because I'm trying to figure out where you got the 120
Mm-hmm.
from.
Yeah.
Minus
So
97, right? And that gives you the difference.
yeah, let me go back here. Stop it. Okay, there we go.
Oh, the threshold. Okay, I see that.
Okay. So I'm going to go here. And all right. So the sensitivity of a JF100E is 97 dB at 1 watt, 1 meter. How powerful will your amplifier need to be to get 100 dB at 10 meters? Okay, so if I need 100 dB at 10 meters, I will need more than that at 1 meter because I will lose a certain amount traveling 10 meters away. So I will need more than 100 dB at 1 meter. So how much would I need at 1 meter? Well, 10 meters and 1 meter, that's a 20 dB difference, isn't it?
Yes.
Yeah. So I will need 20 dB more, right? So that's 120. So I need 120 dB at 1 meter. That's my target. So how do I get 120 dB out of this loudspeaker? Well, I don't know, but I know how to make 97 because the manufacturer told me how. I only need 1 watt of power to make 97. So I can get rid of that. Minus 97. That gets me 23. So I got to get 23 dB more sound, and I need to do it with power, otherwise known as watts. So I need a power ratio here. And a power ratio is 10 to the power of dB divided by 10. So 10 to the power of 23 divided by 10. You run that through your calculator, you get 19 or 199.5 something, right? So that's the power ratio of 23 dB. You multiply that by the power that you used to get that 97 dB. And to get that 97 dB, I used 1 watt of power. And the math whizzes in the room are going, Jason, you don't have to do that step. You're just multiplying by 1. I'm going, yeah, but you're not always going to multiply by 1. Sometimes you will start at different power levels. It just so happens that you're starting at 1 right now. Okay? So don't let yourself get in the habit of skipping that last step. Because if you get in the habit of skipping that last step, and then you end up with a situation where you're starting at a value different than 1, you will not be able to get the right answer. So Force yourself to take that last step of, oh, okay, I started with 1, so times 1 equals 199.5 watts. 200 watt amplifier. Okay? And that's it. That is decibels. That is how they work. And the important thing to remember is that decibels are not actual values. They only describe change. So they describe the difference between two things. They are not an actual value. And they do not progress linearly. Okay? If you start trying to do real math on them, like multiply them, for example, you will not get anything meaningful out of that. Okay? Because it's just describing the difference between two things. It's not describing an actual value. It's only possible to use decibels to describe an actual value if we can somehow agree upon some starting value that we will compare everything against. And we do that all the time, by the way, and that's what we'll learn about on Thursday. But it's important to remember that decibels are just measuring change. They're not measuring actual values. It's not a real number. It's an approximation that's showing the difference between two things. And you can measure the difference between whatever two things you want. And maybe it can be sound, but it can be whatever else, whatever you want. You could measure the difference between, I don't know, anything. Absolutely anything at all. Okay? We tend to use it to measure sound, but it can be used to measure anything. Radio stations use decibels to express the power output of their antennas, broadcast antennas. Electricians use decibels to express the differences between, different circuits and stuff. It's a way to kind of talk about some big difference in actual levels and express that in a smaller number that is easier to talk about. Okay? Because otherwise we'd be saying, turn it up by 28 million pascals. And you'd have to find that on the knob.
Or could we just say turn it up yourself?
Yeah, I mean, people who don't really understand decibels will say, turn it up a little bit, or turn it up just a skosh, or just one notch louder. Take it down a notch. What does that even mean? I have no idea. But decibels is some agreed upon comparison that if we all understand it, we can use that to communicate to each other. And I can say to my A1 who's mixing the show, you mixed that person a couple dB too hot. So take them down 2 dB next time. Great. Now that mixed person knows exactly what I want. I didn't say, oh, that was too loud. Take it down next time. Take it down by how much, right? A smidge. What does that even mean? I don't know. But if I say, take it down 2 dB, okay, they know exactly what to do. And sound equipment is labeled in decibels. And so it's very easy to just go 2 dB. Boom, done, right? And if you do ear training and you train yourself to recognize those decibel differences, then you can know what you're talking about when you say turn it down 2 dB. You will be able to visualize how big of a difference that will be, right? So that's a big reason why we have you do ear training. One of the many reasons is so that you can kind of start putting into your brain those comparisons, so that when you have to talk to somebody about it like that, and you can say, take it down 8 dB, you know what that means, and you know what that's going to sound like when they do that, okay? And you have to be able to do that. Unless you're working all by yourself, which maybe you will sometimes, but if you're working with other people, you have to be able to talk to them and give them instructions using words that they can act upon. And, a little bit, I don't know what that means. How much is a little bit? How much is half a bit? How much is a whole bit? And how much less than that is a little bit? I don't know. Yeah, what's a wee bit? Is that less than a little bit or more than a little bit? Yeah, I don't know.
What's your concept of a bit?
Exactly. So this is why decibels is useful. Okay, other questions? Is this making sense? Ish? Okay. All right. So you've got enough information to do a lot of those practice problems now. So we just need to, on Thursday, we'll talk about reference levels, which is just, mutually agreed upon values that we compare everything against. And we'll talk more about that on Thursday. Eric?
Can we use this inverse square law to solve like the peak power handling ones on the test?
Well, that's power. So that's something else. That's power decibels. I'll take you through some of those on Thursday. All right. Other questions? Yes.
Question not so much related to this. The videos that you take,
Mm-hmm.
you said you do plan on uploading them?
Have I not uploaded any of these yet? Nice.
No, they're the ones from I think it's 4 or 5 years ago, and it's like.
It's the same thing.
Yeah,
Yeah.
it's the same thing.
I haven't changed it dramatically. Okay. Yes, I will endeavor to upload this one.
Thank you.
The problem is if I leave here before I upload it, then I always think, oh, it'll take me forever to do this from home because it's a big video. So I have to do it from campus or it takes forever.
Just upload it right now. We have
Yeah.
a couple minutes left in class.
So I will do that right